with things in this one, we will talk about the definition of a limit of a function. So let's say we have this limit as f of x, where x approaches some value a, and that will equal to L. We're considering the case where L is a finite real number, a is also a finite real number, so we're not taking, now we're looking at some limit that will equal to infinity or something. And so we'll specify that hereby, and also furthermore, we'll use in a second epsilon delta for the definition of it, are all belonging to real numbers as a parentheses. We will use this information all along, that won't change. If you're confused about something, you could always refer to this, look back at this parentheses and see if that helps. So this definition says that as x inputted into f of x approaches a, then the value of f of x will approach L. That's the definition of a limit. But the definition of a limit in this formal way is basically that the limit as x approaches a of f of x equals L if and only if. And now let's write out the definition itself. And this can be formulated in many ways, because we could define something like a neighborhood and then look at that as a set, and through that, name all the things that put together the definition. Or we can just use absolute values, because those will actually suffice for the definition, and logical symbols and less words. We could also use a more worded definition with more words combined with math symbols, or we can just use more strictly logical symbols, which we'll do in this one. So namely, the definition goes as follows: that for any epsilon above 0, and this will in practice mean any very small epsilon that's positive. We've already defined it's real. Now furthermore, we define it's positive. The same will happen in a second with delta. So both epsilon and delta will be very small. We will look at them mostly as small. Well, they must be real, they must be positive. So all along they're positive real numbers, and they are strictly not 0. They're strictly positive, not 0. But they will be seen as very small gradually. So for any epsilon higher than 0, there exists a delta higher than 0 for every x. And now it depends from where to where f is defined. Let's define it from S to R, reals, where R is some subset of reals anyway. So perhaps the input values x for f of x are not all real numbers. There's some real numbers that cannot be, or it could be all real numbers. We haven't specified what f of x is concretely. Perhaps f of x cannot have some real numbers inputted into itself, but output we say it's into the real numbers. So for every x in the input set, we specify s for f. We say this f, by the way, that we're doing this limit of, has this goes from the set that's subset of reals into reals, and then basically for every epsilon above 0 exists some delta above 0 for all x's inside the input values of the function, such that, and now there will be a big parentheses connected to all this. These preconditions on the same level, now these big parentheses, and inside this fundamental logical statement based on an implication that if we have the absolute value of x minus the point that x should approach within that limit definition is smaller than delta, that will imply that the difference between f of x and L is smaller than epsilon. Now, why this matters is we'll go for very small deltas and epsilons in these considerations in order to when imagining it. Okay. Now, it might be useful if one didn't have this intuition before to look at the graph of a random. It's very general. Okay, this is by no means representative of all the cases that we could consider. But let's just say this is one of them. Why limit would exist? Here we have point A, and here we have L. We see this means a whole. It means at x equals A, f of x is not defined. It cannot be inputted. A cannot be directly inputted, but some values very close to it can. And the epsilons and deltas are the small real numbers that can create this so-called neighborhood. We've not defined it, but we can show what it is here. Basically, that means that A will be inside an interval defined by A minus delta until A plus delta. So delta left of A until delta right of A, there's this small interval around the point A, which itself cannot be inputted, but this small points close to it should be very similar in value to A. and then L will have below it slightly and slightly above it, even less far. If we draw it like that, it seems they're already far enough. L plus epsilon above it, and L minus epsilon below it. So L minus epsilon, so epsilon below and epsilon above. From epsilon below until epsilon above, this interval around L will be the neighborhood around L defined by epsilon. Now, delta and epsilon don't necessarily have to equal to each other. They can have ratios. We're not going to go into that. But that depends on the function, that depends on the concrete case we're considering, and so on, what kind of limit concrete we'll be taking. Here we're very general. So for that, basically what it means is that whatever epsilon I take from the neighborhood around the limit actual value of L, anyhow small that epsilon is, because that epsilon is what defines how small that neighborhood is. So for any real number epsilon, anyhow small though, real number epsilon, that will define this small neighborhood around L. So anyhow close with LIM, there will exist delta for around the input value A, the possible supposed one, which perhaps cannot be put into f of x. Perhaps it can. We can also have a limit if it was defined. Okay, I'm just saying for a more general case that it doesn't have to be defined at it. So that it would be necessary. Right here we really see that the function we cannot put the input there. Anyway, for any such epsilon, we can go back. So actually, we're looking here in the definition. We're looking from the outside, from the output, and we're then guaranteeing a certain property around the input values. So we're saying for every epsilon that's higher than 0, which concerns, as I here draw finally, for this the output values for neighborhood, there will exist some small. This will be small, some small delta. Again, that will define this small neighborhood around the input values. All right, for all x's inside the input values of f, and then this further basically says such that there's this implication between these two statements. All right, so as long as basically what this absolute value, if you work it down and look through it, what it basically says that some x's within the neighborhood are close to A by delta, which can be arbitrarily small. That implies that some output values of f of x for those x's that are very close to that A will be by epsilon, by a very small epsilon close to that limit value L.